Let me just briefly share my screen. All right, so welcome everyone to the 42nd ECS and Cloud Feedback Virtual Symposium. Today we have three speakers. We have Margaret Duffy from UC Berkeley NCAR talking about atmospheric mechanisms of the pattern effect. We have Lazaros Oreopoulos from NASA Goddard Space Flight Center, one model, one perturbation experiment, many cloud feedbacks. And we have Andrew Williams, one of our conveners from Princeton GFDL, saying, how do convective mass fluxes respond to warming? And we're going to go in that order, so Margaret will start off today. So we're going to have three short talks, about 13 minutes, with questions after each, and a short general Q&A if there's time remaining. Please type your questions or comments into the chat at any time. And at the end of the talk, if you'd prefer to ask your question live, please raise your hand. We'll unmute you. We're always looking for speakers, so if you're interested in sharing your work at a future symposium, please reach out to any of us. Our emails are in the announcement email. Great. So, Margaret, do you want to start?
All right, how's that?
Looks great. Perfect.
Okay, awesome. Okay, so thank you all for having me here today. I'm going to be talking about mechanisms of the pattern effect. This is work that I did with Brian Medeiros, Andrew Gettleman, and Rob Wills. So I'll go through this. This is my outline. I'll start with a very, very brief reminder of what the pattern effect is, although I know this audience doesn't need it. I will talk about kind of a walk through the literature that I took trying to understand in detail what the mechanisms of the pattern effect are. And then I'll tell you about what I learned evaluating the mechanisms of the pattern effect in Camp 6 and then over the historical period using observations and reanalysis. And I'll summarize by just kind of synthesizing to what extent this changes our thinking about the mechanisms of the pattern effect. So just as a reminder, the pattern effect is important because it's related to this idea that the feedback parameter evolves over time. So this is showing from Senior and Mitchell in the year 2000 that if you abruptly quadruple CO2 concentrations at year 0, the magnitude of the feedback parameter lambda goes down over time. Today we tend to throw a negative sign around this. So we would have this be becoming less negative over time. And we think that this is due to the evolution of the pattern of sea surface temperatures over time. So this map is showing us if you take the SST averaged over a later part of an abrupt 4 times CO2 simulation minus the SST averaged over the first 20 years of an abrupt 4 times CO2 simulation, we tend to get this change in the gradient over the tropical Pacific, which we think is responsible for this evolution of the feedback parameter over time. We often measure this phenomenon using delta lambda. So that's if you average the feedback parameter over, say, the first 20 years of your 4 times CO2 simulation and the last part of your 4 times CO2 simulation, if you take that difference, that gives us delta lambda. Again, sorry about the sign convention here, but typically this would be negative, and if delta lambda were positive, that would mean that the feedback parameter was decreasing in magnitude or becoming more, the feedbacks are becoming more amplifying over time. And so we can see, taking a closer look at this figure, that in the CMIP5 and CMIP6 models, the delta lambda is pretty robustly positive, meaning that the feedbacks are becoming more amplifying over time. All else equal, that would contribute to an increase in the climate sensitivity over time. But with very, very large intramodal spread in that delta lambda. So this is related to the idea of kind of committed or unrealized warming. And an implication is that any estimates of the climate sensitivity that we make using historical data will be underestimates. Okay, so the uncertainty in the delta lambda, to my way of thinking, comes from 2 different sources. One is uncertainty in the pattern of warming, especially that zonal SST gradient, and also uncertainty in how the atmosphere responds to a given pattern of warming. And this talk is focused on part two, but part one is also incredibly important. So the way that I am going to study this is using patch experiments in CAM6. These are pretty standard patch experiments, part of the GFMIP protocol. CAM6 is the community atmosphere model version 6. It's the atmosphere model that goes into CESM2. And we run these patch experiments with 2K amplitude all over the globe. One thing that is unique about this ensemble of patch experiments is that we ran it with the COSP satellite simulator turned on, which allows us to take a closer look at the cloud feedbacks. I won't do that in this particular 15-minute talk, but that is in the forthcoming paper. So just we want to compare this new ensemble of CAM6 patch experiments to previous patch experiments. So I just put CAM4 here on the left. And we can see these are different plotting conventions, but generally the same basic features of a stabilizing influence of warming in the West Pacific and an amplifying influence of warming in the East Pacific emerge robustly. So this is just a nice reassurance that CAM6 patch experiments are broadly consistent with previous patch experiments. Okay, so from here, I wanted to know, okay, what's setting this pattern and why does it look like this and what are the mechanisms? And there are a lot of really nice papers about this, but I wasn't getting like a super clear, consistent picture. So let me walk you through that next and show you why I was so motivated to take a closer look at this question. So here's our little, I'm trying to figure out what the mechanisms are. So here's our little legal pad with notes. In 2016, a paper by Stevens coined the term pattern effect. And in that paper, they attributed the mechanism of the pattern effect to changes in the atmospheric circulation, which respond to geographic differences in warming. And presumably the atmospheric circulation that they're talking about there is the Walker circulation. This is the zonal overturning circulation in the atmosphere, which is balancing this zonal SST gradient. This is the same zonal SST gradient that we know to be evolving over time and yielding the delta lambda. And so there's ascent in this warm West Pacific region associated with high clouds and subsidence over this cooler East Pacific region associated with low clouds. And so we think that that's potentially a mechanism. And so if we look in our patch experiments, and this figure is a little confusing, let me walk you through it. But if we measure the Walker circulation strength using the difference in vertical velocity profiles averaged over a West Pacific box and an East Pacific box, the anomaly in that difference in vertical velocity profiles, if you warm in the West Pacific, is in purple, and the anomaly in that difference in vertical velocity profiles, if you warm in the East Pacific, is in green. So what this is telling us is that if you warm in the tropical West Pacific, you strengthen your Walker circulation, and if you warm in the tropical East Pacific, you tend to weaken your Walker circulation. Okay, so this looks good. Let's put that on our list. What else? So in 2017 and 2018, the pattern effect was related to tropospheric stability. And this is really because the low clouds in those tropical subsidence regions are very important they have very strong feedbacks. And very strong changes with warming. And so that's on the y-axis here is the cloud fraction. And we can see that on the x-axis here is lower tropospheric stability. These things are very correlated. And so here's our sort of simplistic diagram of how tropospheric stability works. But if you have an increase in stability, that tends to trap these low reflective clouds, which have a stabilizing effect. Whereas if you decrease the tropospheric, or if you decrease this d theta dz, you tend to reduce those thick reflective low clouds. Okay, so in our patch experiments now, we can take a look at our theta profiles, and we can see that if we warm the tropical West Pacific region, again, this is an average of the profile over all of the subsidence regions from warming just the West Pacific region. That in general it becomes more stable, whereas if we average those profiles in an experiment where we warm just the East Pacific region, it tends to become less stable. So let's throw that on our list of potential mechanisms. And then in 2023, the circus tent mechanism was introduced, not to explain the pattern effect per se, but to explain the asymmetry between warming and cooling patches. And the idea here, just as a reminder, is that, of course, deep convection is like your tent pole, and your free tropospheric moist static energy is like your tent fabric. So if you have an anomaly in a region of deep convection, that anomaly will be communicated higher up to the free troposphere via that deep convection and impact your free tropospheric moist static energy. And that free tropospheric moist static energy can be communicated laterally via the weak temperature gradient approximation, gravity waves. And so therefore, if you warm in a region of deep convection, you get this very non-local impact of your warming, whereas if you warm in a region of not deep convection, you'll just get a very local impact from your warming. And if we look at this in our patch experiments, we see indeed that if we warm, this is our H star 500, and if we warm in just the West Pacific region, we get an increase in H star 500, not only right over where the patch is, but also laterally, consistent with the weak temperature gradient approximation. Whereas if we warm in this East Pacific region, which is not a region of deep convection, we don't get much movement on H star 500. Okay, so throw that on our list. Okay, so now we have these three proposed mechanisms. We have absolutely no reason to think that these are independent from one another. But hopefully at this point it's clear why I wanted to take a closer look at each of these three mechanisms. Are they related to one another? Are they working? What's going on? Tropospheric stability, to the extent that there has been a prevailing explanation, I would say has probably been the prevailing explanation. But the circus tent model is also very appealing. An early paper alluded to this Walker circulation strength, and it was also my personal hunch going into this. And so what we're going to do here is we're going to basically take a look at each of these three mechanisms in Camp 6 and briefly over the historical period. And what I've done here, okay, so this is our DRDSST from Camp 6 that we saw already. And what I've done here is just using a statistical framework, decomposed DRDSST into the contributions from the three mechanisms from our yellow legal pad. And when we do that, we get an estimate of DRDSST that looks like this, which if you squint is fairly close to our actual DRDSST. And when you multiply each mechanism, which has been put through the Green's function machinery, by the regression coefficient, you get a decomposition of B into the contributions from each of the three proposed mechanisms. And we can see that my hunch about the Walker circulation was totally wrong. And rather, the circus tent mechanism and the stability mechanisms are playing pretty big roles. The circus tent, especially in the regions of deep convection, and the stability mechanism sort of weakly everywhere. Okay, so circus tent and stability mechanisms are dominating, to put it briefly. Let's take a look at what's going on. How am I doing on time? Yeah, over the historical period. Obviously, we can't do patch experiments in the real climate system, so we are going to look at interannual variability instead. And we're going to look separately at the relationship between SST and each of the three mechanisms, and then the relationship between each of the three mechanisms and TOA radiation anomalies. So when we look at that first half of the question, we have SST anomalies on the x-axis, each of the three mechanisms on the y-axis, and ERA5 reanalysis and observations are in green. We can see that all three mechanisms are showing some response to interannual variability in SST. This is reassuring. We expected this. But if we look now at the relationship between each of the three mechanisms and TOA radiation, we can see that there's actually not much going on with the Walker circulation strength. The TOA radiation is not really responding to variations in the Walker circulation strength, but it is responding to variations in the circus tent and stability mechanisms, which is nice. So again, circus tent and stability mechanisms are coming out. I was not expecting the model and the observations to be so consistent with one another, but it's nice that they are. Okay, so what does all of this mean? We had two mechanisms come out, but are they correlated with one another? And indeed they are. Here we have this tropospheric stability on the x-axis and the circus tent on the y-axis. This is an interannual variability. Green is ERA5. They are correlated with one another. And at first I was kind of like, oh, womp, I made a statistical model with correlated predictors. I did use a regularized regression I should have said that earlier. But actually, I think that these things being correlated are meaningful. People who have thought about this more than I have probably realized this already, but the way that I waved my hands when I was introducing the stability mechanism and the way that I waved my hands when I was introducing the circus tent mechanism are different. And so it's worth taking a little bit of a closer look into why these two things might be correlated with one another, since we have a little bit different pictures of how they're working. Um, and we can get some insight into this by just taking a look at our temperature profiles here. And we realize, okay, if LTS is the difference in theta between 700 and the surface, that if we can gain some insight by looking at whether LTS is more influenced by theta 700 versus more influenced by the behavior at the surface. And so when we decompose the impact of stability on radiation anomalies, we can see that indeed it's the interannual variability in theta 700 that the delta R is responding to, not the interannual variability at the surface. So that suggests basically that LTS has non-local control for purposes of the pattern effect, not local control. And we can then imagine that theta 700 should be very closely related to H star 500. It might be affected by the same gravity waves and weak temperature gradients at 700 as at 500. And we realize that, okay, LTS is changing non-locally via this circus tent mechanism. So I think we've kind of synthesized some of our proposed mechanisms and gotten a clearer picture as to what's going on here. And I think the next exciting step about this is potentially actually coming back and constraining delta lambda, which I'm hoping to do soon. And especially I think H star 500, we have some theories about how that works. And so I think this potentially opens up an exciting avenue of research and constraining delta lambda. I think I'm out of time here, so I will just leave my summary slide up. Thanks.
Great, thanks, Margaret. If folks have questions, you can either raise your hand or unmute yourself or put them in the chat. Christy?
Hi, Margaret. Great talk. When you were doing those regressions against stability and theta or radiation, you're using annual values, right? Annual averages?
Do you mean here? Oh,
No,
in the
this is for the
interannual
Green's
variability.
function. Yeah.
Yeah, these are annual averages.
Right.
From
So this is then going to be dominated by ENSO variability.
Mhm.
And whether it's theta 100 or theta 700 that controls more the variability, that's going to depend on where the SST variations are, if they're in the East Pacific or if they're in the West Pacific. And those patterns of SST variability are going to be very different on different time scales. With interannual variability, most of what you're capturing is the ENSO pattern. So just something to think about as annual timescales, Green's functions, historical, you're going to be capturing different patterns of SSTs that are going to be driving different circulation patterns or changes in different regions.
Yeah, totally. That's a great point. And I think that that's a kind of a nice argument for using both model experiments and these patch experiments, which are agnostic, right? About, they're not necessarily reflecting. And so, whereas interannual variability is. So yeah, that's a nice point. Thanks.
Osamu?
Margaret, considering that these mechanisms are correlated, have you looked at the spatial map of these contributions, like the nonlinear terms in your decomposition? And does that, including that, capture some of the discrepancies between your actual DSST and your linearized estimate?
The short answer is no, I haven't looked at that, but I think it's an important question because there are some differences here between A and B. And basically to the extent that there are differences here, this is either due to a mechanism that wasn't on our yellow legal pad or nonlinearities. And I think bisecting that is an interesting question. So yeah, thanks. I think that's a good idea.
Thanks.
Cool. And there's I think a pretty short question in the chat, Margaret, and then we'll move on. Are the CAM6 screens functions available, or will they be made available to use?
They're part of the GFMIP protocol, so they'll be available through GFMIP. And if anybody wants, they're on Glade. So if anybody who has access to that system wants to send me an email, I can give you the path.
Awesome. All right.
Awesome,
Thank you,
thank you.
Margaret. Lazaros, do you want to start sharing your screen?
Yep.
Okay.
Does it look okay?
Yeah, it looks great.
Yeah, thanks. So thanks for inviting me and thanks for being here. So I want to present about how to obtain many cloud feedbacks from a simple perturbation run. And this is work basically that Dongmin Lee, my associate here, has conducted. And he's here for the difficult questions. So, giving you a brief summary here about how cloud feedback can be obtained, either from observations or a model. So the thing, that you probably know, but I'm highlighting here is not the change of the cloud radiative effect, which obviously includes also clear sky in the definition. So what people have done, I think Brian showed and introduced this correction, and Ryan Kramer later implemented it, is basically to take the change in CRE and correct it for clear sky effects and masking effects. Another option is to use the partial radiative perturbation method, but I think what is becoming by far now the most popular option is to use cloud radiative kernels. And this is Mark Zelinka talked about that in the last symposium. So this is good to have that background. If you attended that talk, it's going to help you follow this one better. So the fact that the cloud radiative kernel option is popular is because now in both satellite observations and in the model, we can generate those joint histograms where cloud fraction is distributed among different cloud types. So ECS started this with 9 cloud types, and then they made that histogram more detailed, having essentially 49 cloud types defined by the ranges of optical thickness and cloud top pressure. So in a model, you get these types of joint histograms from the MODIS and ECS simulator, but you need to create the subgrid variability, and you do that via a subcolumn generator and COSPAS, the SCOPS subcolumn generator. So once you have that, what do? You just convolve them with cloud radiative kernels, expressing basically the sensitivity of the overcast cloud radiative effect to a unit perturbation of cloud fraction. These basically, the ones I'm showing here are coming from Mark Zelinka. So these were calculated by using offline calculations, basically putting different clouds in prescribed atmospheres. I think the latest version coming from Mark is the one that used reanalysis cloud atmospheric fields. So once you convolve them, once you convolve the cloud fraction anomalies, from your experiment with the cloud radiative kernels, you basically get, cloud feedback. So Mark explained all this pretty well in the previous symposium. So this is kind of the background, and let me tell you specifically about what we did. So we have the GEOS model, which is not a model usually used for climate experiments, but this is the one we have access to. So I give some information about the version, we used. It's very important here that, that model has the RTMG radiative transfer scheme that operates with the Monte Carlo independent column approximation. So we performed an ME4K basically experiment from which we calculate the feedback by looking at the cloud anomalies and multiplying them with the kernel. And we'll look at this as a function of the global air temperature perturbation, which for this experiment, for this period of 15 years, was 4.69 K. So let me talk about the kernels, first, what kernel options, we have. So these are the offline kernels I talked about that we get from a radiative transfer model and, the different cloud types that we put in different atmospheres. So this is probably the most popular choice for people to get cloud feedback from models. But lately, there's been another option available, and that's from observations. Series has a product called the Flux by Cloud type product that essentially gives you broadband fluxes at the pixel level, at the modest pixel level. And there is a paper that describes how this is happening. So now you can have, for each cloud type, basically, you can have the overcast radiative effect that corresponds to that. And you can build kernels, and you're going to see, the patterns obviously they're going to be pretty similar in this phase space because they express the fundamental physics of how the cloud radiative flux depends on the cloud type, on the combination of cloud top pressure and optical thickness. But the individual values are different. Now, here we have a third option, and this is enabled by the fact that in the GEOS model, we run the Makaica independent column approximation. So we have to generate a subgrid cloud field, and we essentially calculate subgrid radiation a similar way that you get from the observation at the pixel level. It's like our subcolumns are basically pixels, and we have cloudy radiation at the subgrid level. So while we run the radiation, we can collect those subgrid radiation values and basically resample them later in the form of a joint histogram. And you see, these joint histograms we get, these cloud radiative kernels we get from the model on the fly are quite a bit different than, the ones that were pre-calculated or seen in the observations. So we're going to be using, in a calculation of cloud feedback, 3 different radiative kernels. But now let's see if we have choices in building our joint histograms on which these are going to be operating. So you have the classic SCOPS subgrid cloud field that you get by passing a profile of cloud fraction and mean optical thickness. So you can apply maximum random overlap. You can select that, and you see, these generate cloud fields that have vertical inhomogeneity, but horizontally, you have a homogeneous cloud. So from those cloud fields, you can build your joint histograms. And now you have 2 choices, right? You have the ESCAPE simulator and you have the MODIS simulator. And you're going to see that the joint histograms you generate are quite different. You have a lot of high thin clouds as in the ESCAPE observation. So I guess this is by design, which you don't have in the MODIS simulator. The low clouds are pretty similar. The MODIS simulator, on the other hand, has many high clouds elsewhere, not in the thinnest bin. And you would see the overall cloud fraction is quite different. This is because the MODIS simulator ignores everything that's below 0.3 optical thickness. But what we did, the new thing that we did is we introduced in SCOPS another subgrid column generator from Ryzen in 2004 that applies generalized overlap. And you will see this is a much more complex cloud field because not only is the overlap different, but we allow for horizontal variability in the optical thickness. We basically have a parameterization of variance as a function of cloud fraction. So each layer has its own PDF of cloud optical thickness. So we can aggregate those in histograms through the ESCP and MODIS simulator. But if you compare the lower row of panels with the upper row, you see that the generator doesn't make that much of a difference for this particular model. It's mostly the simulator, that we use that creates the biggest difference. Finally, we have the option of not using a simulator at all. We basically create the subcolumns for the radiation, and we aggregate them in the form of the histogram because we know what the cloud top pressure and what the optical thickness of each cloudy subcolumn is. So we have 5 different histograms in 3 different kernels, and basically we can create 15 different types of feedback. And here I'm showing results from the most popular choice, which is people have been using the ESCP simulator with the SCOPS subcolumn generator and the histogram it produces. And at the top, we have kind of the newest, which is the model's own cloud radiative kernel, and using basically the RTMG kernels. And you will see here that the overall perturbation of the cloud fraction is quite similar, but the distribution is different. And even though the shortwave cloud feedback overall is very similar, you see its distribution in this phase space is quite different as well. Similarly in the long wave. So here is the most kind of popular choice people have been using, and here's the one that's kind of our newest thing using the model's own CRK. If you look at the patterns, the amount patterns are pretty similar, but you have some differences in the optical thickness feedback. But a lot of the pattern is driven by the underlying mean properties at the grid cell level that the model provides. So again, I have our newest, and one could consider perhaps the best and the most kind of popular choice. But the thing I guess this is, the main plot of this presentation is those 15 feedbacks that I can get from the 5 combinations of joint histograms and 3 radiative kernels. So I have the total feedback broken into LED, long wave, and short wave. And this can be further broken into amount, altitude, and optical thickness. If you look at Mark's paper, he introduced that decomposition. There is a small residual term here. And I want to point your attention to the range of different cloud feedbacks you get. So the most popular choice, ESCP with SCOPS, ESCP simulator with SCOPS, and our newest thing. So you see they're pretty far apart. And if you look at this range, is about 0.7 watts per meter square. So you go from 0.4 to 1.1. And this, to a large extent, comes from quite a wide range in the components. So you have a large range, and but the top plot where you get the net feedback is basically the sum of the individual feedbacks here. So we wanted to look at whether when you sum those individual feedbacks, you get some cancellations here. So we're looking into the similarity of the individual feedbacks between the 15 different choices that we have. So we'll look at this matrix, the RMS of basically the 6 independent feedbacks that we have. So we took our latest and greatest as the reference, and then we'll look how different are those individual feedback components to the reference. And you're going to see what matters here more in the similarity is having the same kernel and having basically the same simulator. If you use a different subcolumn generator, is not going to make much of a difference. So 15 different values of feedback, some of them are alike and some of them are not. How am I doing with time?
A little bit, 2 minutes.
Okay. So here are my conclusions. So potentially there's many ways to create subgrid cloudy subcolumns in a global model. I showed you only 2, Ryson and simulator and Scope's simulator, but people can come up with their own subcolumn generator. You know, the resonance simulator is limited to the generalized overlap that doesn't have minimum overlap, for example. So one can build, you know, potentially a more sophisticated subcolumn generator. The other point I want to make is, unless you want to compare with observation, you know, you can build, you know, a cloud fraction joint histogram. There's nothing to do, you know, with a simulator, right? Your feedback shouldn't be depending on your observation system, although there is the motivation that you want to compare a model feedback with an observed feedback, in which case using a simulator makes sense. But I also want to point out that now there's multiple options to create cloud radiative kernels with the traditional offline calculation, of course, but also from observations. But the new thing here is that we can create one on the fly because we have subgrid radiation in the model. So for GEOS, we generated 15 cloud feedbacks for a particular ME4.K experiment. So one question that remains is that if you were to use a different model with those, and you would apply those combinations, would you get a narrower or a wider range of feedbacks? Because both the creation of the histogram and the creation of the subcolumns depends basically on what the underlying mean cloud field is in the model. So I'm going to leave it at that. Thanks.
Great, thank you so much. So if folks have questions, please either raise your hand or unmute yourself and feel free to ask, put it in the chat. We have a question from Mark, if you want to unmute.
Yeah, nice presentation, Lazarus. I was just curious, do you know why the on the fly GEOS long wave kernel is so weak compared to the others?
You are probably referring to
This one here.
this area here, right?
Yep.
So I think it has to do, so this is a global annual average that is not being used anywhere, right? This is kind of like for display purposes. So I think what's going on here is the lack of basically, it's the combination of cloud types with environment, right? So I think what's happening is probably you putting the high clouds only in a humid environment and not in a dry environment, you know, having its top of the atmosphere effect being weaker. So I think is where clouds are happening in the model as opposed to your offline calculation where, you know, the same cloud goes everywhere essentially, and what you see in the observations. So if the model has a bias about where clouds are happening and what atmospheres they're combined with, you can get those discrepancies. I think that's the more plausible explanation.
Got it. Thank you.
Any other questions? Well, in the interest of time, I think we'll probably move on because we have about 20 minutes left. So thank you, Lazarus, for the nice presentation, and we'll move on to Andrew. And feel free to continue putting questions in the chat if you have further questions.
All right.
Looks good.
You see me? Great. Okay, 1 second. Cool. So yeah, I'm going to talk a little bit today about some work I've been doing during my postdoc so far at Princeton and collaborating with Nader. And the big question we've been trying to answer over the past year or so is, how do convective mass fluxes respond to warming? And some people may not even know what convective mass fluxes are. So let's get on the same page first. So what I'm going to do is I'm going to ask you to imagine that you're on an airplane on a flight through the tropics and you've paid extra for a window seat. Let me give myself a laser pointer here. So if you looked out the window, you may be lucky enough to see some clouds that look something like this. And you've got a towering cumulonimbus here, you've got clear skies elsewhere. And if you were to take a slice through the middle of the atmosphere, you could decompose the motion that you're seeing in this cloudscape broadly into two categories. So on the one hand, you have intense cloudy updrafts, which are in strong regions of upward ascent, but they cover only a tiny fraction of the tropics, like less than 1% of the tropics is covered by these cloudy updrafts. And the rest of the air can be thought of generally as slowly subsiding environmental substance, which is pretty weakly descending, but covers basically all of the tropics. And it turns out when you average over the whole of the tropics, for example, what goes up must come down. So the mass per unit area, per unit time that's being fluxed upwards in these convective towers, that's MC here, must be equal to the mass that's coming down per unit area, per unit time in these gray arrows. So this is the convective mass flux, MC here. So it's just defined as the density of air times by this 1% number times by the strength of the ascent, and then that must be equal to the subsidence mass flux in the clear sky regions. But sigma here is just 1 because it basically covers all of the tropics. And this convective mass flux is a really fundamental quantity in tropical dynamics, and it's really important for understanding how tropical circulation responds to warming. So that's why people care about this quantity. And so when people start asking questions like how do convective mass fluxes respond to warming, their minds often go first to this seminal paper by Isaac Held and Brian Soden in 2006. And what they did was in this paper was introduce a conceptual model, which I've sketched on the side here, which talks about the journey of an air parcel. So the idea is that you can think of parcels of air as being moistened by evaporative fluxes in the boundary layer. And then those parcels get transported from the boundary layer up into the free troposphere, associated with some mass flux at that interface. All of that moisture then precipitates out, and those parcels return completely dry. That's the conceptual picture. Now, in the tropical mean, what that means is that all of your precipitation is just coming from moisture that's being fluxed from the boundary layer up into the free troposphere. So you can write that P equals MQ, where Q is the boundary layer specific humidity, and M is the mass flux at this level. And because we're interested in the mass flux itself, you can rearrange this equation so you get M equals P over Q. And in this 2006 paper, Isaac and Brian introduced an argument for how mass fluxes should then respond to global warming. So the idea is that we know based off theory and models that precipitation in like a tropical or global mean increases pretty slowly with global warming, only about 1 or 3% per Kelvin. But boundary layer specific humidity goes up with Clausius-Clapeyron, so it goes up at like 6 or 7% per Kelvin. And so if this equality is to hold, then mass fluxes need to decrease with global warming. And this argument, like basically what's on this slide right now, it's ubiquitous in the literature. So this argument appears in IPCC reports and thousands of papers by this point, arguing for how mass fluxes should respond to global warming. And when I started the postdoc, I had a pretty simple question, which is just, does this work? And so to test that, I went to the RC-EMIP archive, which is coordinated by Allison Wing at Florida State. And basically what these simulations are is they're a set of doubly periodic high-resolution cloud resolving models. So lots of different modeling centers ran this radiative convective equilibrium setup where you get this popcorn convection, sometimes people call it. So you get convective updrafts just bubbling up here, and they run over different SSTs. And what you can do in these simulations is you can calculate the convective mass flux at each level by just asking how much air is this convective tower moving upwards, basically. And you could do that for different SSTs and look at the response to warming. Now, so now we can test this P equals MQ scaling in these RC-EMIP models by plotting the diagnosed changes in convective mass flux on the y-axis against P over Q, which is the prediction. And if that worked, you would expect a lot of dots along this one-to-one line. But what you actually find is that although the Held-Soden scaling consistently predicts a decrease of about 2 to 3% per Kelvin, the models actually simulate a very wide range of changes in convective mass flux under warming. And some models even even predict an increase in convective mass fluxes under warming, which is contrary to this P equals MQ scaling. So what went wrong? This all seemed pretty straightforward so far. So let's go back to this conceptual model. So we had parcels of air being moistened, carrying the moisture up, the moisture becomes precipitation, and the parcel returns dry. Now, the key addition, the thing that's missing here is that these parcels actually don't return dry. So when these parcels of air return to the boundary layer, they're carrying some moisture with them still. And so precipitation is actually the flux of moisture into the free troposphere minus the flux of moisture out of the free troposphere. So you can write that as P equals MQ, and then with this extra factor, which is just 1 minus the relative humidity at this level. And we can test this in RCEMIP as well. So this is the same, basically the same plot as I showed you a second ago. So this is the cloud-based mass flux change with warming against the P over Q scaling. And it doesn't do super well here. But if you do this other version where you include the 1 minus RH factor, then you drastically increase your skill of your ability to predict these mass flux changes. But the problem is that now all of this skill is coming from changes in relative humidity at the cloud base or the lifted condensation level. And this is a very unconstrained quantity. So, it varies between -5 and maybe +5 or +6% per Kelvin. And we don't have a theory for this. Like, no one understands how this relative humidity at this level should respond to warming. We typically assume RH is constant, right, under global warming. So this drastically, I think, limits the usefulness of this scaling, even though you can make it work. And then one more thing I just want to talk about briefly is, some people, when I show them this, goes, well, what about the original paper? So in the original paper, there is this plot which shows in this dotted line, basically the P over Q scaling, and then in this solid line, the fractional changes in mass flux, subgrid mass flux from the GFDL CM 2.1 model. And you can see that these track pretty well, and that's taken as verification of the P equals MQ that I talked about a second ago. But nowadays we have many more models with PQ and subgrid M to make this plot with. And you can see, so this is a reproduction of that original plot here. And then basically what you see is that P equals MQ predicts a decrease in mass flux in blue in all of these models. But the models actually simulate, again, very wide changes in mass flux, and they don't always follow as well as they do in this CM 2.1 model. So this original verification doesn't appear to be a robust source that something that we can take a lot of confidence from when we look across models. And so I think what I take away from all this is that we need a better theory. We need or at least a different theory for thinking about convective mass fluxes under warming. And that's what I'm going to try and briefly introduce to you here. So what we're going to do is we're going to take a different approach. We're going to appeal to this mass balance that I talked about a second ago. So what goes up must come down. And so what this tells us is that the mass flux is just equal to the subsidence mass flux, which is a function of this subsidence vertical velocity. So what this tells us is if we know the downwards velocity of these gray arrows, then we automatically get an expression for the convective mass flux. And we can get an expression for this subsidence vertical velocity by looking at the thermodynamic equation in clear skies. So it ends up being a pretty simple equation. And basically it just says that the subsidence vertical velocity is equal to the radiative cooling divided by the difference between the dry lapse rate, which is just say 10 or something, minus the true lapse rate, which is a moist adiabat. So we can plug that in, and now we get an expression for the convective mass flux at any level now, not just at cloud base, any level in the free atmosphere. So it's, again, the radiative cooling divided by this lapse rate term. Now, how do these different portions of this equation respond to global warming? So under warming, the atmosphere becomes moister, you have more latent heat release. And what that means is that this lapse rate term here the lapse rate becomes more stable, and gamma becomes a smaller number. So you have 10 minus a smaller and smaller number, and this whole thing that I've circled becomes bigger under warming. So all else equal, the lapse rate is acting to weaken mass fluxes under warming. But what about the radiative cooling on top here? So this is the big conceptual leap that we're going to make. So to understand radiative cooling, what we're going to do is we're going to take this expression that we had a second ago, and I'm going to rewrite the radiative cooling in this form. So this F now is just the net upwards radiative flux, and this is a partial derivative with respect to temperature here, as opposed to maybe pressure or height. And on the bottom, you have a lapse rate term, which looks a little bit different, but it still just increases with warming. So you're still just dividing by a bigger number here. Now, you may say, why on earth have you done that, Andrew? This looks way more complicated. And the reason I'm doing it is because based off some fairly fundamental radiative transfer physics, it turns out that this form of radiative cooling on the top only cares about the local atmospheric temperature. And so what that means is if you use temperature now as your vertical coordinate, as opposed to, say, height or pressure again, this form of radiative cooling looks basically exactly the same no matter what your surface temperature is. So let me just say that one more time. So this form of radiative cooling on top only cares about the local temperature. So if you know that your parcel is, say, feeling 240 Kelvin of temperature, this form of radiative cooling will basically always be around 0.8 or something, no matter what the surface temperature is. Now that tells us that if we think about convective mass fluxes now, with temperature as our vertical coordinate, so going from the surface at 300 to the tropopause at, say, 200, then these convective mass fluxes should decrease with warming in temperature coordinates. Now, the reason for that is, again, because on the top, we have a thing that doesn't change with warming. And on the bottom, we still have this lapse rate term that's increasing with warming. So you're just constant thing divided by thing that gets bigger. And so there's a lot of math here. I don't like to put too much math in my talks, but this is all we'll really need. And we've arrived at this prediction about how mass fluxes should respond to surface warming. So we can, again, test this prediction across RC-EMIT. So what I'm doing here is I'm just plotting the changes in convective mass flux from the warmest simulation to the coldest simulation as a function of height. And you can see here that these are an inconsistent sign in the mid-troposphere. So the models really predict either increases or decreases in convective mass flux at a given height in these simulations with warming. Now,
2 minutes.
Thanks, Matt. Now, if we take this exact same data and we just plot it with respect to temperature as the vertical coordinate rather than height, what we find is that all of these models predict a decrease in convective mass fluxes with warming if you just look at a specific temperature in the atmosphere. And this is a big tick for this prediction that we had a slide or two ago. This confirms it across a wide range of models. But what you see is that although we've now constrained the sign, there's still a huge range across these simulations. There's a factor of 2 or 3 spread. And it turns out that a lot of this spread is coming because these models disagree on the baseline profile of convective mass flux before any warming has happened. So now, rather than looking at absolute changes, let's normalize by this and look at fractional changes. And what you find is that fractional changes across all of these simulations are very highly constrained. And these RC-EMIP simulations, although they agree on almost nothing else, like convective aggregation and relative humidity are all over the place, it seems like they can agree on convective mass fluxes decreasing by about 4% per Kelvin when in temperature coordinates. And I don't have very much time left, but just very quickly, where does this 4% per Kelvin come from? So it turns out you can take this expression that we had a second ago, and you could take the derivative with respect to surface temperature, and you get this expression here. So this is the fractional changes in mass flux at a given isotherm is related to changes in the lapse rate here. And this just encompasses the holistic thing that I told you at the beginning, which is that if the lapse rate weakens, then this is a bigger number you're dividing by. This is just the math version of what I said there. And so you can plot those two contributions. So this is the actual change in convective mass flux, and this is the contribution from these lapse rate changes. You can see they line up pretty well. And in the tropics, we have a good theory for the lapse rate. The lapse rate is basically a moist adiabat. So if you work through, you can make an analytical theory for what this term should look like based off just a moist adiabat. And it looks pretty good. So based off of just simple theory, we can predict where this roughly 4% per Kelvin number comes from. So in conclusion, convective mass fluxes decrease with warming if you look in temperature coordinates, and they do so at a rate of about 4% per Kelvin, which is just because of the basic stabilization of the lapse rate. And I finally just want to say that I think that we should be careful when we try to reason about climate change using the P equals MQ scaling, because there's a lot of, like I've shown you here, there's a lot of ways in which that can potentially lead you astray and is maybe not robust across models in the way that we perhaps thought it was. So yeah, thanks very much. And if you want more details, we have a paper in press at James.
Awesome. Thank you, Andrew. Any questions for Andrew? Feel free to raise your hand, throw it in the chat, unmute yourself. Karsten, I think, went first.
Yes, if I may. Great talk, Andrew, as always. Always also how you give this explainer so that everyone is on the same page. It's really cool. Appreciate it.
Thank you.
And yeah, cool topic. Which begs one question which may or may not be related, and it's about the cape. So there's this concept of E-cape, entrainment cape. So you do have entrainment, even though it might not be treated as such in models. Can you comment on that? How do models actually, or do you know whether they do have entrainment? And if so, does it matter? Would it change any of what you are doing?
Yeah, I think models try to represent entrainment in different ways. And cape does still go up in those models, whether you do look at E-cape or just normal cape. Turns out, so like I said, the lapse rate is you can treat it as just a simple moist adiabat, but there are also forms of the equations for the moist adiabat which include entrainment. And you can do the whole game that I did again with that, and you get a very similar number. So at least for what I'm showing here, entrainment is not doesn't make a huge difference to this result, not in terms of the lapse rate component, at least. They're in the paper, there are a few more details to this theory, which I didn't have time to talk about, but there are other places entrainment can enter through microphysical components of this theory, but they're slightly second order. So yeah, thanks for the question.
Great, that's what I thought. Thanks.
Rob?
Thanks, Andrew. Really nice. So I was wondering about this breakdown of the Helton-Soden framework due to changes in relative humidity. You showed it based on RC EMIP. I'm wondering about basically how large these fractional changes in relative humidity can be, because it's easier to get a large fractional change of relative humidity in a fairly dry climatology than it is in a when the near surface boundary layer is near saturation. So I was wondering if there's any mean state bias in relative humidity between RC EMIP and something more like the real world. And therefore, do we need to worry about this breakdown quite as much in more realistic simulations, or how do we bring this understanding into a more realistic context in RC EMIP?
Yeah, that's a really good question. So yeah, the relevant quantity here is 1 minus RH. So actually so you get a bigger, so for a given delta RH, you get a bigger fractional change if it's mean state bigger, more moist. And yeah, there is a potential here that RC EMIP is maybe moister than the real world, and therefore these changes are amplified compared to what they might be in a slightly more realistic setup. I've just downloaded the RCE large simulations, which have these have aggregation and drier patches. So I'm going to test this again in RCE large and see if it looks, because that will account for the fact that they're generally drier simulations than RCE small, basically, when they aggregate. So that'll be the test there. The other thing is it's difficult to kind of define some of these quantities in a more realistic simulation. We have global storm resolving models at GFDL that I've been looking at, but precisely what you call the LCL and things like that, when you're trying to do a tropical average, is quite tricky. So there's just logistical issues with applying this framework to really realistic simulations. But yeah, I'm going to try aggregated ones.
Awesome. And I think maybe we had a question from Jonah, but we're a couple minutes past the hour, so maybe if you wanted to hang on, Andrew, and Jonah had that question for you. But otherwise, thanks again to all of our speakers, Andrew, Lazaros, and Margaret, and we'll see you next month.
Thank you.